Okay, Ken, if you are ready, I think we can start. You're ready?
Yeah, sure.
Okay, so it's very nice to have Kévin Nguyen today from Harvard, who will talk us about, tell us about superluminal chaos and after a quantum quench. So please, Kévin, whenever you want.
Thanks, Daniel. Yeah, so first of all, I would like to thank and congratulate the organizers for putting together this series of webinars. I already benefited from it by watching some recorded videos, so that's very nice. So the talk today is based on a paper from last year in collaboration with Vaidya Balasubramanian from UPenn and Ben Krabs and Marine de Klerk from Vrije Universiteit Brussels. And the topic is quantum chaos in holographic CFTs. And in particular, so far, well, much work has been done on computing probes of quantum chaos, such as commutator squared and out-of-time ordered correlators in the case of thermal states. And here we will go a bit beyond that and consider some time-dependent holographic state, which is basically a thermal state which undergo at some at some moment in time undergoes a global quench and subsequently thermalizes. So this is basically the topic. So here is a rough overview. So as I mentioned, one probe of quantum chaos is this commutator square that you can see here. And so if you wait long enough, if you wait for times that are larger than the inverse temperature in the system, or which is also called the dissipation time, then when you unpack this commutator square, there are various 4-point functions, but most of them factorize into the product of 2-point functions, except one which survives, which is the out-of-time ordered correlator. And in a quantum chaotic system, we expect this commutator squared to grow exponentially with time. And since we know that 2-point functions at finite temperature do not grow exponentially, but rather decay exponentially, this exponential growth can only come from the OTOC. So this is the quantity that we will be looking at. And in particular, I want to explain how to compute those OTOC from the gravity picture in the context of ADS-CFT. So there was already a formula that was originally given by Shenker and Stanford from 6 years ago. But I will provide an alternative formula, which is based on the geodesic approximation to field propagation in ADS spacetimes. And this will yield a very intuitive picture where you basically compute the OTOC by computing the 2-to-2 scattering of particles in the bulk of ADS. So that will be one part of the talk, and then I will apply this alternative formula that we provide in order to compute the OTOC in global quenched states. So yeah, and so this is the gravitational picture that we have in mind. So we have at early time some black hole, some BTZ black hole with some horizon radius R minus. Then at some moment in time, we inject dust matter from the asymptotic boundary. which falls into the bulk and is absorbed by the black hole, which subsequently grows to some larger horizon radius. And this is due to some state, to some thermal state in the dual CFT, in which we inject energy at some moment in time, and which subsequently thermalizes to some higher temperature. Okay, now when we will apply the formula, when we will compute the OTOC, in this case, we will find this result. So these are the level sets of the OTOC. The, let's say, operator V is inserted at the origin. And well, this plot describes the value of the OTOC for, well, as a function of the operator of the insertion point of the second operator W. And so this horizontal black line is the time of energy injection. Before that, we can see that this red line has slope 1, and this defines for us the butterfly velocity. So the butterfly velocity is initially the speed of light, but right after energy injection, well, we see that the slope becomes less than 1, which means that the butterfly velocity becomes superluminal. So that's yeah, and I will explain that in the second part of the talk. So is there any question before I go on? So please interrupt me at any time if you have any question. Okay, so let me start with some general introduction so that everybody is on the same page. So first of all, let's talk about chaos in a classical system, such as this Lorentz attractor. So we will say that a classical system is chaotic if a small variation in initial conditions leads to widely different trajectories at some later time. So, and this will be, I mean, the mathematical criterion for this is the following. So you look at the position of the system at some time t, and you vary with respect to initial conditions. And if this quantity grows exponentially with time, then you say that the system is chaotic. And this exponent lambda L is called the Lyapunov exponent. Now, as you can see, you can rewrite this quantity as the Poisson bracket of the position and at time t and the momentum at well, at initial time. So when you go over to the quantum realm and you want to find an analogous quantity that diagnoses a quantum chaos, it's very natural to want to replace this Poisson bracket by the commutator of two Hermitian operators and take the expectation value in some CFT state of interest, for example. But we know that the expectation value of a commutator is simply the linear response in the system. And at finite temperature, this decays exponentially, where the decay constant is basically the temperature, rather than exponentially growing. So we need to find another quantity. And Larkin and Ovchinnikov, long time ago, proposed such a quantity, which is simply the square of the commutator. And indeed, when you compute this in a quantum chaotic system, you generically find that this grows exponentially with time. So it seems to be a good probe of quantum chaos. Now, as I already said, if you wait long enough, in particular, if you wait for times that are larger than the inverse temperature, then this commutator squared factorizes into the product of two-point functions, which are well known, and this out-of-time ordered correlator. And if the commutator squared grows exponentially, it can only come from the OTOC contribution. So we can simplify, I mean, we can restrict our analysis to the computation of this guy as a first step. And I should also mention that this exponential growth, this Lyapunov growth, does not last forever. In fact, at some point, there is a transition between exponential growth and saturation of the commutator squared. Or in terms of the OTOC, there is a transition between this well, exponential regime and a decay regime. And the time scale at which this transition occurs is by definition the scrambling time. So yeah, this defines for you what the scrambling time is. Okay, yeah.
Can W and V be any operators constructed out of the field variables, or should there be, because in the classical case you showed that the Poisson bracket was between the canonical position and momenta, right?
Yeah. So here, in principle, it could be anything, but with the restriction that these operators should be simple, like constructed out of simple local operators, and they should be small perturbations of the system.
Okay, thank you.
Yeah. But okay, to go from the Poisson bracket to this commutator squared, it's more of a guess, of an educated guess rather than like some formal quantization procedure.
Yeah, that answers my question. Thank you.
Okay, great. Okay, so now we're okay. Perhaps I should also first mention the interpretation that you can give to this commutator square. So, in particular, one way to think about it is that it measures how much of the information initially contained in this perturbation V scrambles into some other degree of freedom W at some later time t. And right, so the bigger this quantity, the more information has been scrambled into this other degree of freedom. Okay, so now we go over to the context of ADS-CFT. But before like computing this OTOC in gravity, I want to give a very heuristic and intuitive argument from which we can understand where the exponential growth in the OTOC comes from. So we're working at finite temperature, so there is an ADS black hole. And now if we look at the 2-to-2 scattering of particles in the neighborhood of this black hole and compute the center of mass energy of the collision, this appears to grow exponentially with the time separation between the boundary insertions. So here E in is the conserved energy of the ingoing particle. E out is the conserved energy of the outgoing particle. And this factor is nothing more but a blue shift factor associated to the, well, acceleration of these particles in the black hole background. And the more you have, well, the bigger the time separation on the boundary, the more time those particles have to accelerate into the gravitational field before interacting with each other. And you can easily convince yourself that this exponent here should be the surface gravity of the black hole, or equivalently should be the temperature of the black hole. So this is a very heuristic way to understand where the exponential growth comes from. But I will derive this from first principle in the following. Okay, so as I mentioned, 6 years ago, in a very nice paper, Shenker and Stanford proposed a way to compute these OTOC from the gravity picture. And the first step is to realize that you can compute this 4-point function well, evaluated in a thermal state as the overlap of two states. One would simply be this state here. So it's the state that we see here is the thermophile double state, which is dual to neutronal BTZ black hole, where you insert some V operator at the boundary, time t1, followed by a W insertion at time t2. And the other state you need to consider is basically the same thing, but you have to revert the order of these two operator insertions. Now, Shenker and Stanford proposed to represent this state as an out state on some future Cauchy slice, which is taken to be actually the future horizon of the black hole, and to represent this state as a nil state on some initial Cauchy slice, which is taken to be the past horizon of the black hole. Now, the OTOC is the overlap of those two states. So basically, it's the transition amplitude for going from this configuration to this configuration. Okay, so applying this reasoning, they arrive at this expression for the OTOC. So let me describe what goes in there. There are 4 psis, and these psis are basically the boundary to horizon propagators, because you want to represent well, this state as an in state, for example. So you want to propagate, let's say, W of t4 backward in time onto the past horizon. But then you also have to take the Fourier transform along the u coordinate of the horizon. So basically what you do, you decompose, well, you represent this state on the past horizon, and you decompose the wave function into right moving momentum modes. So you do you play a similar game for well, all insertions, and then you proceed to the transition amplitude in momentum space. So you proceed with the 2-to-2 scattering amplitude of momentum modes that scatter along the horizon. Okay, and this, well, and the transition amplitude is simply given by this iconal phase factor in the high energy scattering limit. Okay, so perhaps one comment that may be important is that this formula assumes that the time separation on the boundary is very large compared to the inverse temperature. Otherwise, you wouldn't expect the scattering to happen at the horizon itself. It would happen somewhere in the bulk, but away from the horizon. Okay, so this explains this very nice formula, where you still have to perform several integrals. So you have to integrate over the momenta of the wave functions, so Pu and Pv, but also over the transverse coordinate x prime and x second prime, because, well, although you have, let's say, inserted T4 at some locally on the boundary, when you propagate it backward onto the path horizon, it spreads well, in transverse direction as well. So you have to take that into account. Okay, so applying this nice formula, Shenker and Stanford obtained the commutator squared in the case of the thermal state or the static BTZ black hole. And they indeed find a very simple exponential growth, where the Lyapunov exponent is 2 pi times the temperature of the thermal state. So in particular, it saturates the so-called chaos bound derived by Maldacena, Shenker, and Stanford. And the spatial dependence, so the spatial dependence comes from the transverse separation of the operator insertion on the boundary. So this spatial dependence defines for you the butterfly velocity, which in this case is just the speed of light. Okay, so here I'm looking at the level sets of the commutator squared. If I look at zero spatial separation, there is exponential increase with time up to the scrambling time, which is which happens around 10 on this plot. At which point there is a transition between this exponential increase and saturation. And so then you follow the line of value 1 for the commutator squared, which is this red line, and this defines for you the butterfly velocity. So the velocity at which the region where information has been efficiently scrambled. Sorry, so so this describes the growth of the region where information has been efficiently scrambled. Okay, so any question at this point? Okay. Okay, so now let me go to our own work, where we, so one of the results is that we provide an alternative formula to compute OTOC in gravity, and the reason that we did so is that we want to go beyond the limitations of the previous formula. So in particular, we don't want to rely on Fourier decomposition. This is only useful when you decompose on some Cauchy surface that has translation invariants, such as black hole horizons. And at the same time, we don't want to assume a large time separations compared to the inverse temperature. So these are the two main reasons. So I will proceed in 3 steps. The first step is to describe the geodesic approximation to bulk propagators. The second is to, using this geodesic approximation, compute time-ordered bulk 4-point functions. So this is the 2-to-2 scattering part of the computation. And then construct from that the out-of-time order correlator. Okay, so let's start with the geodesic approximation. So we have in mind some primary operators V and W in the dual CFT, which are dual to massive fields in ADS. So these massive fields, they satisfy the Klein-Gordon equation. And the geodesic approximation is basically a WKB approximation in the large mass limit. So what you do is that you write an ansatz for the solution as series expansion in 1/n. And if you're only interested in solving the Klein-Gordon equation at leading and subleading order in 1/n, then you can assume this form. So phi will be the product of some amplitude that does not scale with m and some phase factor which oscillates very rapidly due to this the appearance of this m. And there is also, of course, some function s that sits there, which does not scale with m. So now you plug this in the Klein-Gordon equation, and at leading order in the large mass limit, this is what you find. So first of all, you define the vector k mu as the derivative of this function s. And then the Klein-Gordon equation tells you that k is time-like. And in addition, you can show that this vector k mu satisfies the geodesic equation. So this means that the phase function s is simply the action of a time-like geodesic connecting this point x of interest. And the other point is an integration constant that you have to fix from by boundary conditions. And you can solve order by order in 1/m, and you will find some equation for A, and can proceed in this way, but we won't need the information about A for our purpose. Okay, so now let me tell you how to compute this kind of 4-point time-ordered 4-point functions in the bulk. So here we have 2 insertions at the boundary and 2 insertions in the bulk, which are anchored on some future Cauchy slice and past Cauchy slice, which are the analog, if you want, of the future and past horizons in the Shenker and Stanford construction. But here we can take, we can take any Cauchy slice. Okay, so we want to compute this kind of 2-to-2 scattering, and I will do so by using the path integral representation, where the dynamics of the system is basically the Klein-Gordon dynamics of the fields phi W and phi V, which are dual to the W and V CFT operators, plus the gravitational dynamics, the Einstein-Hilbert action. Okay, so I write down this time-ordered 4-point function as a path integral, and I explicitly perform the phi w and phi v integrals, which directly give me the time-ordered 2-point functions of the Klein-Gordon fields. But I still have to integrate over all possible metrics. Of course, this is a bit too difficult, so I'm gonna plug in right now the geodesic approximation for these 2-point functions. So I'm gonna replace this 2-point function by some amplitude times some highly oscillating phase factor, where S of W is the action of a geodesic connecting the 2 insertion points of this 2-point function. Similarly for this other 2-point function, so I get to this simplified version. And now I can perform this integral by saddle point approximation in the weak gravity limit. So basically, what I have to do, I have to find the metric G mu nu, which extremizes the sum of these 3 exponents, and evaluate the integrand on shell. But so extremizing this is basically the same as solving Einstein's equations sourced by two geodesics. Okay, so the solution will be of this form. It will be the sum of some background ADS metric that satisfies prescribed boundary conditions and perturbations, which are basically the gravitational fields of the 2 particles that are propagating in the bulk. And there are in principle higher order corrections, but we will truncate this to linear order. Okay, so now I have to compute the on-shell action, which will be the on-shell action associated to the background. And at linear order, something very nice happens, is that you recover the iconal phase shift that you would get from computing the 2-to-2 scattering of particles in ADS by looking at all ladder and cross ladder diagrams and resumming them. You get exactly the same expression. But in this classical derivation, what we have to do is to simply contract the gravitational field emitted by the V particle with the stress tensor of the W particle, and vice versa. So this piece, this iconal phase shift, knows about the gravitational interaction of the 2 particles in the bulk. Okay, so in summary, what we find for the time-ordered 4-point function is the following. It's just the product of the Klein-Gordon 2-point functions, some phase factor that is irrelevant because it's common to all amplitudes that you would compute in ADS, and this iconal phase factor, iconal phase shift, which knows about the gravitational interaction of 2 highly energetic particles. Okay. Okay, so now I can go over to the construction of the out-of-time order correlator. And the logic is very similar to that of Shenker and Stanford. So I want to represent, well, I want to compute the OTOC as the overlap of 2 states. very much in the same way as we did before. And for that, I will propagate one pair of operators to some future Cauchy slice sigma u naught, and the other pair of operators to some past Cauchy slice sigma v naught. And for this, you can use Green's second identity. So, for example, here I have written the phi v of x1 operator as an integral over the phi v operators on the future Cauchy slice, well, convoluted with appropriate propagators. So, for example, psi prime, this state here, would take this form. And so you play a similar game for a psi. You take the overlap of the two states. And what you find is that you basically need to compute the time-ordered correlator that we were looking at right before. But you have to convolute that with appropriate propagators. So basically, you have to propagate one of the phis back in time onto this Cauchy horizon, propagate forward in time one of the phi v operators onto the future horizon, compute the 2-to-2 scattering, then undo the propagation, and you have to integrate over the Cauchy slices. Okay, so that's basically that's basically it. So this is a position space analog of the Shenker and Stanford formula. Okay, but since we are using the geodesic approximation, I can further simplify this expression. So I replace the 4-point function and, well, the time-ordered 4-point function, and we have this exponential I delta which appears. And I replace the propagators by amplitudes times phase factors. And the phase factors would disappear if I did not separate both W operators on the boundary by some small time epsilon plus. And similarly, here I separated the V insertions on the boundary by some small time epsilon minus. Okay, so these phases here are basically what remains from the phase factors of all 4 boundary bulk propagators. So to apply this formula, what one has to do is to compute, well, is to look at all geodesics that emanate from the boundary insertion points and connect the future and past Cauchy slices in the bulk. Compute the 2-to-2 scattering for each pair of ingoing and outgoing geodesic. Compute the conserved energies of this geodesic, and then integrate over all points on the Cauchy slice. Okay, so this is still too difficult for us. So we'll do it by saddle point approximation. So that means that you have to find the one pair of ingoing and outgoing geodesics in the bulk which extremize those phase factors. And once you've done that, then the OTOC basically simplifies to this iconal phase factor. evaluated for this dominating pair of geodesics. So okay, so this is, I mean, this is the basically the end a formula that we propose in the geodesic approximation and in the saddle point approximation. You see that it's very compact. And before applying that to any case, we can already see how the exponential Lyapunov growth will appear. In particular, if you restrict to times that are smaller than the scrambling time, by definition, that means that you're looking at delta much smaller than 1. So when you go to the commutator squared and you expand in delta, the first term that you find is delta squared. And okay, let me remind you what delta is. So delta is this quantity, so it knows about the gravitational interaction of the two geodesics in the bulk. And in particular, it will always be proportional. Delta will always be proportional to the center of mass, or the square of the center of mass energy of the collision. So this is probably a good time to get back to this picture that I had in the beginning, where I explained that well, in the presence of a black hole, the energy of the collision grows exponentially with the time separation on the boundary. So just from that, you can already estimate what's going on with the commutator square. Okay, any question at this point? Okay. Okay, so what are the advantages of this new formula? Well, first of all, it's very compact, very intuitive, as you can see. But it also does not rely on the assumption that the time separation is much bigger than the inverse temperature. So in particular, you can look at the zero temperature limit of the commutator squared. And what you find using this alternative formula is a quadratic growth instead of an exponential growth. So there is no temperature, so this is, we don't expect exponential growth. But we find instead this quadratic growth. And in fact, it agrees with results derived by Roberts and Stanford using CFT computations. Okay, so with this new method, we can make contact with this so-called slow scrambling at zero temperature. There is, however, one limitation, at least one limitation that I can think of our approach, is that at least in the current state, it does not describe the late time saturation of the commutator square. So it does not describe the transition between exponential growth and decay of the OTOC. And the reason for that is that with the geodesic approximation that we use, we were not able to describe the late time quasi-normal decay of boundary bulk propagators. But in principle, this can be studied. I will give one more comment at the end. Okay. Okay. So now we have this new way of computing OTOC, and we're going to apply it to a quench state in the CFT, or in gravity, we're going to look at this BTZ Vaidya spacetime, where you start from some black hole at some initial temperature, and then you inject dust matter from infinity, which means that the black hole will grow and heats up to some higher temperature. And we're going to compute the OTOC in this background. So there are various configurations of operator insertions at the boundary that you can think of. If you put the operators on the same side of the energy injection, well, you will recover the thermal result, because this quantity is not sensitive to the energy injection. But if you put your operators on both sides of the energy injection, then you will be sensitive to this energy injection, and well, you will be sensitive to the thermalization of the state. Okay, so I'm gonna skip. Sorry, I'm just looking at the time. I'm gonna skip all computational details. These you can find in the paper, but I'm just gonna give you the result. So what we do is that we compute this OTOC in the geodesic approximation, as I described. So for that, we need to find the one pair of geodesics which extremizes this overlap integral, and compute their iconal phase factor. So for that, we have to compute the gravitational field emitted by each of the particles, and then contract these gravitational shock waves, actually, with the stress tensors of both particles. Okay, so it turns out that the dominating pair of geodesic is simply, well, the dominating geodesics are simply those which fall radially from the boundary. So that's pretty simple. But to show that it was okay, it was not that easy, but that's the end result. So here is the result, approximate result. You can find some more complete expression in the paper. But basically, you see that before energy injection, so Vs is the time of energy injection to the system, you recover the thermal result. So that's good. But if you look after the energy injection, you find that you find this modified expression. And if you look at the time dependence, you see that the Lyapunov exponent is basically the temperature, the late time temperature. So we have, I would say, local saturation, well, saturation of the local chaos bound. So the exponential increase will always be sensitive to the local temperature. So before the quench, the temperature is R minus. After the quench, it's R plus. So that's one thing. Here, this factor is basically the amount of exponential increase of Lyapunov growth that that happened before energy injection, so between 0 and Vs. And so after that, we have this other Lyapunov exponent. But we are also interested in the spatial dependence of the commutator squared. So here you can see the level sets of the commutator squared for 2 different times of energy injection. So the black horizontal line is the time of energy injection. You indeed see that before energy injection, this is just the thermal result. But after energy injection, this line, this red line, which indicates well, the extent of the region where scrambling has been efficiently performed. This red line, well, go from unit slope to some smaller slope. So it means in particular that the butterfly velocity becomes superluminal right after energy injection. In fact, you can compute what the butterfly velocity is right after energy injection. It's the ratio of temperatures, and it's indeed bigger than 1. Okay, so one can ask, where does this superluminal behavior come from? So if you look at this expression, it's pretty obvious. You have exponential growth in time at the rate r plus, but you have exponential decrease in x at a different rate r minus. So it looks like the spatial dependence is only sensitive to the early temperature and not the late time temperature. And the way to understand this in the gravity picture is the following. So we're looking at this kind of 2-to-2 scattering. Let's say that there is no transverse separation between V and W. Then the interaction basically happens here, where the geodesic cross, which happens in the lower region. So this is why the spatial dependence. Well, okay. Let me go on a bit. So now let's imagine that you increase a bit the transverse separation between V and W. Then the interaction will be shifted forward in time. The reason being that the gravitational shock wave emitted by one geodesic has to travel the transverse space in order to reach the second geodesic. But if the separation is not too big, then this will still happen in the lower region. Now, there is a point at which so there is, if you separate enough the 2 operators on the boundary in transverse direction, then the interaction might happen in the second region of the spacetime. So the gravitational shock wave will have to travel too much distance in transverse direction before hitting the second geodesic, and will actually do so after crossing the null shell. Okay, so but this we haven't analyzed, and it actually coincides with this hashed region on the plots. Okay, so the colored region is where the gravitational interaction happens in the small black hole region, and this hashed region is where there is contribution from the second, the bigger black hole region. Okay, so in summary, to summarize, so the exponential growth in time purely comes from blue shifting effect of the particles. And because the particles spend part of their lives in the small black hole, but also part of their lives in the big black hole, this is why you have two contributions to the exponential increase in time. And spatial dependence comes from a different effect. It's not about blue shift, it's about gravitational interaction. So it's about, yeah, it's about the exchange of gravitons by the two particles. Okay, let me see. Right, and one last point, perhaps, is that so this butterfly velocity is superluminal for right after energy injection, but as you can see, it relaxes as you go to larger spatial separations. So we don't expect any causality violation from this. Causality violation would mean that you would have some colors, so some non-zero value outside of the light cone. And so you see here that there is nothing outside. Okay, so this is basically all I wanted to tell you. Let me summarize. So in our paper, we have provided an alternative formula to compute OTOC from the gravity picture in ADS-CFT. The pros are that these are purely position space. They're applicable to any asymptotically ADS spacetime, which can be time dependent, for example. You don't need any symmetry to apply the formula. And it does not rely on large time separations compared to the inverse temperature. So in particular, you can recover slow scrambling. Now the main con is that at the moment, our formula does not account for late time dissipation, so late time saturation of the OTOC. And for that, in order to account for that, you would need to be able to describe quasi-normal decay of two-point functions in the geodesic approximation. And for that, a good starting point would probably be this paper by Festuccia and Liu. But we haven't done so. So then we applied this new method to the computation of the OTOC in BTZ Vaidya or in some quenched states. And we found local saturation of the Kills bound. We found transient superluminal butterfly velocity. But we don't have the result at very large spatial separations. For that, we would need to compute, well, actually, that's something that is in progress, but we would need to compute the shock wave as it propagates across the shell of matter, which is a bit tricky to do. Okay, and we can ask, of course, what about a CFT computation? Can we match our gravity computation to some CFT computation? We haven't done so, but a good starting point would probably be those papers by Anus, Hartmann, Rovai, and Sunner, in which they describe how to construct quenched states in the CFT. And finally, there are probably many open problems that one can think of, or applications of the formalism that we have developed. So there is this inclusion of dissipation, which I already mentioned. But one other thing that we are currently thinking about, or actually working on, is the computation of OTOC in extremal BTZ, extremal rotating BTZ, and black hole microstates. And since those have zero temperature, it's very important to be able to go beyond the limitation of the original formula by Shenker and Stanford. Okay, so yeah, that's all from my side.
Thanks a lot, Vin. Very nice talk. So we have time for questions. So please, whomever wants to ask a question, just ask or make a comment. Don't be shy.
Hi, this is Matthias. If nobody else wants to ask a question, I can ask one, because I wonder about the geodesic approximation. Can you pinpoint, so I mean, it's in a certain sense geodesics, which are a classical approximation, I understand, to, in a certain sense, to two-point functions, which I take it don't include dissipation by construction. And so do you see, basically two questions, one fueled by my ignorance at least. Do you see a simple extension to include dissipation within that formalism, or do you see, I mean, okay, feeds into my second question. Festucci and Liu, did they not consider the large momentum limit and consider the dissipation and quasi-normal mode behavior at large momenta? Is that the paper that you're citing, or?
Yeah, I think you're right. I think they find the quasi-normal modes at large spatial momenta. Yeah, I think that's right. Yeah, but right. So it may not be possible to recover all poles. I mean, all quasi-normal modes. But okay, in principle, at least those of Festucci and Liu could, I mean, you could recover them. The question is how to incorporate that into the geodesic approximation. And I think that what they describe is that although you think that, well, okay, this is an ansatz, and you have to check afterwards that it is satisfied. In fact, what they describe is that the regime where you see quasi-normal decay for the two-point function is precisely when this amplitude actually competes with this exponent here. So when this is not, well, this is not independent of M anymore. I mean, it actually scales with M. So it's something that they call Stokes phenomenon, if I'm not mistaken. But okay, it would be interesting to actually look at this, but I haven't done it so far.
Okay, thank you.
I have a question.
Sure, yeah.
Firstly, I would like to thank you for the nice talk. My question is about the validity of your assumption, where you considered linear perturbations of gravity to study the geodesic. For me, in the case of the Shenker and Stanford work, it is clear that coming from the dry and toothed ideas, the linear shock wave is also a solution to dynamical equations in the bulk. But in the case of geodesic, I don't have any idea. Could you please?
Yeah, so actually, that's right. So you can show that the shock wave is just the solution of Einstein's equations sourced by geodesic. So I think it's yeah, I think it coincides with what you're saying.
So in this sense, there is no any difference between geodesic approximation or shockwave computations.
Right. I mean, as soon as you have a shockwave, that means that you assumed that you're working in geodesic approximation.
Okay, good. Thank you.
Good, thanks, Navid.
So okay, perhaps one more comment about that is that in the paper of Shenker and Stanford, they don't explicitly mention geodesics, but what they do is that they decompose their wave functions on momentum modes, as I was saying, and then they treat each momentum mode as a particle in the bulk. So that's where the geodesic approximation comes in. So in principle, a momentum mode is I mean, it's a plane wave, but if it's highly energetic enough, then you can approximate this well by the in the geodesic approximation.
Okay, thank you.
Good. Any more questions, comment, last questions? Okay, if there's no questions, let's thank Kévin again. Very nice talk. Thanks a lot.
Thanks for having me.
No, very nice. So let me just say that we have the last talk before August break next week, so in a week from now, by Mario Flori. And as usual, you can find these talks slides online, and also you will be able to find the video. And as I said last time, I'm not going to end the meeting, so if anyone wants to stay here, I will stop recording, which I'm doing now. So